Okay, so we're going over. This is from 2016, number 3. So first off, I want to do kind of a background on what you need to know to do this problem. So to to do this problem, you need to first off know the fundamental definition for electric potential, which is capital V. So the fundamental definition is potential energy per charge. So set up a situation where we can talk about this. So say we have a positive charge and we'll call it capital Q. So in the previous chapter before electric potential, we talked about electric fields. So a positive charge like this is going to be creating an electric field. And all that means is that, so this vector represents an electric field. All that means is if we put a little charge in here, so little q, this little q would experience a force. Now, the fundamental definition of electric field, and we're going to use this when we get to the problem, basic definition for electric field is force per charge. And the direction on everything in physics is based on little positive charges. So notice that the direction of the electric field points to the right. And the reason for that is if you put a little positive charge right here, the force would be to the right. Now, which way would the electric field be up here? Well, if we stuck a little positive charge right here, the force from the big charge, from the point charge on the test charge, would be this way. That's the force of the electric field. So therefore, the electric field at that point is going that way. All right, now, electric potential. So let's pick 2 points in this electric field. So let's call this point point A, and then over here we'll call this point B. A positive charge at point A would have what we call electric potential energy. That's this U right here. And it's very similar to potential energy in a gravitational field. You know, if you have the Earth, here's the Earth, and you have an object above the Earth. This object here would have gravitational potential energy. So in a very similar way, if we released this positive charge from point A, the positive charge would move freely from A to B, and in doing so, there would be a decrease in potential energy. So one thing to recognize here is that comparing point A and point B, point A is going to have a larger electric potential. So I'm going to draw a big V. At point A, there's going to be a larger electric potential, and at point B, it's going to be a smaller electric potential. Now, what's the reason for that? Well, this is our definition for electric potential right here. At point A, the positive charge is closer to the positive point charge, and you know, when we release it, this positive charge wants to move towards point B. So bringing it back to gravity, you know, if we release a mass right here, which way does the mass want to move? It wants to move down, and in moving downward, there's going to be a decrease in the mass's potential energy. So in general, if an object moves in the direction it wants to move, that's going to be a decrease in potential energy. So the idea here is if potential energy of a positive point charge, test charge, so everything is based on a positive charge. If the potential energy of that positive charge decreases, then the electric potential must also decrease. And at the end of the day, really what we're going to care about is change in electric potential. So this equation here is best written as change of electric potential equals change of potential energy per charge. You know, because really what matters is the difference between 2 points. Okay, second equation that I want to talk about is when it comes to, let's clean this up. So when it comes to calculating, so here's positive charge Q, here's our electric field. So let's say we want to go to a point that's a distance r, so a distance r from the charge on this electric field line. And let's say we want to calculate what the electric potential is. So we could go to that point right there and calculate what the electric potential would be. And the equation for doing that, electric potential at a distance from a point charge, the equation for that is KQ over R. And the Q do not absolute value. Do not absolute value in this equation. And I'll explain the reason why. But let's say you're given the numbers, right? Let's say you're given the value of Q and you're given the value of R, and you plug in, oh, and K is just Coulomb's constant, 9 times 10 to the 9th. So let's say the numbers work out really nicely. Let's just say we calculate a value of 10 volt. The electric potential at that point is 10 volt. If we go to a point that's farther away from this point charge, we would expect the electric potential there, plugging into the same equation, we would expect the electric potential here to be less. And the reason why is that Q has stayed the same, but we're now a farther distance, right? If R gets bigger and this stays the same, then we would expect this to be smaller. So let's say the numbers work out super nice and we get 2 volt, right? So let's do a situation. So let's say we put a positive charge here, and let's say that charge is positive 2 coulombs. So if this positive charge moves from, let's call this A and we'll call that B, like that. So if the positive charge moves from A to B freely, you could calculate the change of potential energy using this equation. You could go, the change of potential energy is going to be the change of electric potential, which, by the way, that's called potential difference. And potential difference is also known as voltage. So it's going to be the potential difference multiplied by the charge. So what is the potential difference between A and B? Well, change is always final minus initial. Where did this positive charge end? It ended at 2 volts. Where did it start? At 10. So you're going to go 2 minus 10 times the charge, and the charge was 2 coulombs. So we get -8, and a volt, I didn't mention this yet, but the unit for energy is joule. The unit for charge is coulomb. That's what we call a volt. So this quantity here, 2 minus 10 is -8. That's joule per coulomb. And then we multiply that by the charge that moved across that potential difference, and we get -16 joules. Now, why do we not absolute value this? And this is going to be important in our, when we actually get to the problem we're going to solve. But laying this all out right now is going to make our discussion much, much, much easier. So let's just say that instead of this being a positive charge, let's just say it was a negative charge, okay? If it's a negative charge, well, which way is the electric field going to be? So everything is based on a little positive guy. So which way would the force be? If this were a big negative and that's a little positive, the force would be that way, force of electric field. So the electric field here is going to be directed this way. The electric field is that way. So let's do the exact same thing. Let's go to 2 points here. And let's say again that those numbers work out really, really nicely. In fact, to the same magnitude. So we'll call this point A and that's point B. So let's say we plug into this equation right here. And let's say that we get an electric potential at A of -10 volt. And it should come out negative because do not absolute value that. So we would plug in, whatever this charge is, that gets plugged in as a negative value, which gives us a negative electric potential. Now, Point B, the R is bigger, so we would expect the magnitude to be smaller. So let's just say, again, it comes out as 2. Keep the numbers really nice. So we get the same situation, only now the values are negative. Well, which way would a positive charge want to move? Well, if we stick a positive charge here in this electric field, where would this positive charge have more potential energy? And keep in mind, which way does the positive charge want to go? It wants to go to the left. So where does the positive charge have more potential energy? It's going to have more potential energy at point B, right? We release this positive charge at point B. It is going to move freely from B over to A, and that means that A must have a lower electric potential than point B. And in fact, -10 is smaller than -2. So this is the reason why you do not absolute value in this equation here, because a positive charge, when it moves freely, must go from higher electric potential to a lower electric potential. Okay, third idea here. I want to talk about equipotential lines. Well, actually, real quick, one thing I did not mention yet. This potential energy, let's go to this equation here. Change of potential energy, this change of potential energy is also equal to work. So we can just extend this equation a little farther out. A change of potential energy is going to be equal to the work done. So it would also be accurate to say that potential difference equals work done over charge. Now, why is work the same as potential energy? I mean, you could bring it back to the gravitational field. So let's say here's the Earth and you have a mass on the Earth. If you pick this mass up, right, you're going to exert a force. And in lifting the mass up, you're going to be doing work, right? Because work is force over a distance. Let's say you lift it that high. So it is true that as the mass is lifted, work is being done. And it just so happens that the work being done is equal to the gain of potential energy. And in a very similar way, like let's look at this diagram here, the force of the electric field is to the left. As this positive charge moves down the electric field, we could say two things. We could say that this positive charge has a change of potential energy, and it would be also true to say that the electric field did work on that positive charge. And these two would be equal. Though it would be the same thing. Okay? Third thing, and we're almost to the problem. Let's do a new layer. Okay, last thing I want to talk about before we start the problem are equipotential lines. Equipotential lines, also known as isolines. Okay, so let's look at a situation just where we have one point charge. So there's an electric field going out like this, electric field like that. So what we just talked about is, so let's call this guy charge Q. If we go out a distance R, we can calculate the electric potential at that point. The equation is KQ over R, and we get some value. So let's just say again, like, oh my gosh, we plug in Q, we plug in R, K. Let's just say it comes out as, I don't know, 6 volts, something nice. If we went the same distance R this direction, with charge being the same, R the same, we would get the exact same value plugging into this equation. And then same thing over here. We go out here, same distance R. So what we're finding is, we have these points. If we travel a certain distance R from a point charge, the electric potential is going to be the same. So we can draw in what we call isolines. So that's what this dotted sphere here is. So what So this is an isoline. And what an isoline is where every single point on that line is at the same electric potential. All right, now what if we have multiple point charges? So more than just one point charge. So let's look at what it would be. Oh, you know what? I forgot to mention something. Back here, before we move on, one thing to know about electric fields and isolines. So here's our electric field, and then the dotted is the isoline. Isolines are always perpendicular to the electric field line. Now, why is that true? Why must the isoline be perpendicular to the electric field line? The reason why is it takes zero work to move a charge along an isoline. So let's say we put a little positive guy on this isoline. If we move this little positive charge on this isoline, it requires zero work to do that. That's like the definition of an isoline, because look, our definition of potential difference is change of potential energy per charge. But as we said, change of potential energy is also the work done. If we're moving a charge on an isoline, that means that the electric potential is not changing. That would be zero, which means that the work to move the charge must also be zero, or there's no change of potential energy. Now, it'd be like this. On the Earth, you have a flat surface, and let's say there's no friction, because we can assume that there's these isolines have no friction, okay? How much work would be required to move, and this should be a flat surface, flat, not a hill. How much work is required to move this object a distance d on a frictionless surface? The answer is no work. If this is a frictionless surface, no work is required. This box will move once started, once it's in motion. If it's on a frictionless surface, no work is required to move it, right? Now, what if the electric field were not perpendicular to the isoline? So like, what if this was your isoline? So this represents isoline, and then here's our charge. If the electric field were like at an angle like this, that would now mean in order to move this charge, let's say we're moving the charge this way, we would now have to work against the electric field, right? Because the electric field would now have a component, right? The electric field would have X component and Y component, and we would have to work against this X component right there. Okay, so let's now look at positive charge, so now we have two charges. So the electric field lines here, the electric field lines are going to behave like this. So let's say we put a positive charge. So we're going to figure out what the electric field lines are doing here. So let's say we put a positive charge over here. So a little positive. What's the electric field doing? Well, it's going to be in the direction of force on the little positive guy. So the electric field is like that. Now, what if we put a little positive guy right here? Well, the little positive guy is going to go like that, and that's the direction of the electric field. And then like that, and then like that. Now, how about if we put a little positive guy like right here? So that little positive guy is going to go out like this, and then we have another positive charge over here that's going to repel him. So when the positive charge gets to like this point, this positive charge over here is going to start to repel. So what happens is this guy is going to go up like this. And then how about if we put him down here? He's going to go down like that. And then let's do the electric field lines for this guy. So this guy's going to have electric field line there, electric field line there. These are our electric field lines like that. And then here, very similar. Put a positive charge here. It's going to go up like that. Electric field lines do not cross. Now, we know that isolines must be perpendicular to the electric field lines. So let's start drawing in isolines. So if we're close to this left charge, it's going to be like this, isoline, and we're just going to get isoline going around like that. Now, if we go a little farther out, the iso line is going to go like this. We got to hit it perpendicular, and then hit that guy perpendicular, like that, like that. And then this guy would have one, you know, in like that. Okay, so this is what iso lines look like if the charges are both of the same sign. And it would be true, instead of this being plus and plus, this could have been minus and minus, but then just change the direction on these electric fields, right? Instead of them pointing out, the electric field would point in. Okay. Now, what if we have positive charge, negative charge? So now the electric field, so put a little positive dude right here, the electric field is going to go like that. This little positive guy is going to move from the big positive point charge to the big negative point charge. The electric field behaves like that. Now, what if we put the little positive guy here? He's going to go up like this and then get pulled in to the negative. So there's the electric field line there. How about if we put him there? Little positive guy would go around like that and then in like this. And then out, 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 and then in, in, in. And now we can draw our iso lines. So our iso lines are going to be, so we got to hit the electric field line perpendicular. So we're going to go doot, 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 like this. And then go again. Like that. And then over here. So it's a different looking situation. And then if these guys are oppositely charged, plus and minus, there's going to be a line down the middle somewhere. Not necessarily exactly the middle. It depends upon, are these two charges equal in magnitude? If this guy were bigger, if this positive charge were bigger, then this line down the middle would be off to the right more, closer to the negative. But this line down the middle is where the electric potential is 0. And the reason for that, again, is, you know, electric potential is KQ over R. Do not absolute value this Q. So the way you would find electric potential right in the middle is it's going to be the sum of the electric potential from this positive and this negative. And they would cancel, right? Plus and minus would cancel. So this is what iso lines look like if the charges are opposite. Okay. Oh my gosh, that was a long intro. So let's actually get to the problem. So here is the question. So having done all that, this should be pretty straightforward, or I should say more straightforward now. Okay, so we're given this situation, dots in the figure above, in this figure here, 2 identical spheres, X and Y, fixed in place with their centers in the plane of the page. Both spheres are charged, and the charge on sphere Y is positive. So we know that Y is a positive charge right here. The charge on sphere Y is positive. The lines are iso lines of potential with a potential difference of 10 volts between each set of adjacent lines. The absolute value, meaning they're not telling us plus or minus, the absolute value of the electric potential of the outermost line is 50 volt. So out here, this outermost line is 50 volt, but we don't know if that's plus or minus, but we can figure it out. So let's just kind of diagram. I'm going to diagram what's happening here. So we got charge Y. So here's how you could think about this. So here's charge Y. They told us that Y was positive. So there's an electric field going out like this. So let's label the points. So we got point C, and then there's another iso line right there. And then after that is B, and then there's another iso line, and then there's A, and then there's this point here that we know is 50. This point out here is 50. Now, just think about what a positive charge would experience. So if we stuck a positive charge in this situation, Here's a little guy. So this is the big point charge. This is the little test charge. Where would this little test charge, where would this test charge have more potential energy? The answer is at point C. If we put a little test charge here at point C and release him, he is going to move from C over towards point A and this 50-volt ISO line. So what that means is point C, so the definition for electric potential is potential energy per charge based on a little positive guy. If point C is the location where this positive test charge has a higher potential energy, then the electric potential must be bigger there. So we know that the potential difference between isolines is 10. So that means that A is going to be 60. This next one is going to be 70. This one's going to be 80. This one's going to be 90. And then point C would be 100. Okay, so indicate the values of the potentials at A and B. So A is going to be positive 60 volt, and then B is going to be positive 80 volts. And they have to be positive because Y is positive, you know, and again, the way you calculate electric potential, you know, if you actually came to a point and you're like, hey, I want to calculate what is the electric potential there, the equation you're using is KQ over R, but you do not absolute value Q. So the point being, all of these electric potentials have to be positive according to that equation. Okay. Part B, how do the magnitudes and signs of the charges of the spheres compare? So based upon, so let's start with the signs of the charges. So we can figure out that sphere X has the same sign charge as Y based upon how these isolines look. And according to the answer key to this free response question, they would accept that for an answer. You just say, based upon the shape of the isolines, sphere X must have the same sign charge as sphere Y. Because if that were not true, then we would get the other appearance. Like, so let's just say that X were negative and then here's Y as positive. This is where the isolines would look like this, right? If they were opposite. Oh, and you could also say, so if they were oppositely charged, there would be that isoline down the middle of zero electric potential. In this diagram, we do not have an isoline down the middle with an electric potential of 0, which would indicate that they were opposite. So these two charges are definitely the same sign. And then how about their magnitude? So here's how you want to explain this. You want to reference the equation KQ over R, and what you're going to say is this. So this isoline nearest to X, so this isoline right here that I'm drawing on, that's 100 volt. We figured out that isoline nearest is 100, right? We did that right here. And then this isoline nearest to Y is also 100. So charge Y must be bigger than charge X because the distance to the nearest isoline for Y is farther than the distance to the nearest isoline for X. You could just take this equation, solve it for Q. Solve it for Q. Q equals VR over K, where K is a constant. And for this situation, V is also a constant because the nearest isolines are both 100. So a smaller R is going to indicate a smaller charge. So the distance to the nearest isoline for X is smaller than than the distance to the nearest isoline for y, which would indicate a smaller charge. All right, let's revert this. Okay. Okay, so now we're on to this one. The spheres at point X and Y have masses in the same ratio. Okay, so we're saying mass of sphere X over mass of sphere Y is equal to the charge of sphere X over the charge of sphere Y. So mass ratio and charge ratio is the same. And then they're saying the isolines of gravitational potential for the spheres have shapes similar to those of isolines shown. Explain why the two sets of isolines have similar shapes. Okay. Well, first of all, let me explain what they're talking about. So if we look at mass, okay, if we look at mass, so say instead of these being charges, now say they're masses. So mass X, and then over here is a larger mass Y. So same situation, but instead of them being charges, now they're masses. So masses do not have electric fields, but they do have gravitational fields. So let's just think what would happen if we put a little mass, so let's say this dot represents a little mass, and we put a little mass near mass X. Mass X is going to attract this little mass right here. So there's going to be a gravitational force, right? This would be a gravitational force, and that would indicate the direction of the gravitational field. Now, what if we put a little mass right here? Now the gravitational force is going to be directly towards the center of mass X. That's the gravitational field. Same thing over here. Gravitational field goes like this. Now, what if we put, and keep in mind our system involves two masses, what if we put a mass like out here? Let's put a mass like right here. Now, if we put a mass right here, both mass Y and mass X are going to be exerting forces on it, but this mass is closer to mass X, and the end result is going to be this mass is going to come down like this and into sphere X. And then same thing over here. If we put a mass here, it's going to go in like that. And then over here, very similar, we're going to have a gravitational field line, gravitational field, gravitational field. And then if we put a mass like, let's say, out here, it's going to go into mass Y. And notice this is very similar to what we had for electric field lines. So now we can draw in our isolines, right? Because again, all an isoline is it's a line where the potential energy remains constant, right? So the isoline for this gravitational situation is going to be like this. And then if we move farther away, let's go a little farther away. So here's our isoline, and we got to hit perpendicular. So we hit perpendicular there. We end up getting a very, very similar shape situation. Right? Now, how do we explain this? So we recognize that the isolines are similar. So how would we explain this? What I would say for this question is I would say two masses, so these two masses, mass X and mass Y, will attract a third mass, meaning like this guy or this guy. So these two masses, mass X and mass Y, will attract a third mass in the same way that these two charges attract a third oppositely charged test charge, right? So we put a little negative here. A little negative guy is going to be attracted to these. It's going to get pulled in like that. If we put over here, it's going to get pulled in like that. Okay. Then you could also mention that both gravitational forces and electric forces, they're of the same form, okay? They're of the same form. So we're not onto that one yet. So you would say, to answer this, you're gonna say, so first thing you're gonna say here, number one, you're gonna say two masses will attract a third mass in the same way that two charges of the same sign would attract a third charge of opposite sign. And then the second thing you could say is that both gravitational forces and electric forces are of the same form. The way you calculate gravitational force is Gm1 m2 over r squared. And the way you calculate electrostatic force is Kq1 Q2 over r squared. So they're of the same form. All right, question C. Based on your answer to this one, briefly describe one similarity and one difference between electric and gravitational forces exerted on the proton by the system of two spheres. Oh, and they set up a situation for us. So now what they're talking about here is, so point A, the electric potential at A is going to be VA. The electric potential at B is going to be VB, and then VC. And then a proton of charge Q and mass M is released from point B. So this first question, so we want similarity and difference. Okay, that's actually a really easy one. So similarity, I'm just going to use this right here. This is your similarity right here. The similarity between gravitational forces and electric forces, they are of the same form. Both the gravitational force and the electrostatic force, the equations almost look identical. They're the result of multiplying. For gravitational force, you multiply the masses. For electrostatic force, you multiply the charges. And then both forces are proportional to the inverse square of the distance from charge between the charges, right? R squared. So that's how they are similar. And then for difference, what you're going to say for difference is that electric forces can be attractive or repulsive, right? So charges can attract or repel. Gravitational forces are only attractive. Hi, Lily. Hey, you know what? Can you give me like 2 minutes? Oh, thanks, baby.
This is Zoom?
Yeah, I'm actually I'm recording a problem right now. Do you want to say hi to everybody?
Hi, bye.
Okay, so differences. Okay, that's good. Let's go to the next one. Okay, at point, question D. Okay, so question D. At some time after being released at point B, so here's our diagram for the situation they've described. So we have charge Y, let's say, and we have these points. So here's our electric field. So here's charge Y. There's an electric field going through these points. So I'm just going to simplify this over here. Okay, so we have this first point, which they're calling VC, and then there's another iso line, and then we have a point here called VB, and then there, and then VA, and then this last point they told us was 50 volt. But for this problem, everything's going to be variables. So they told us that the proton was released at point B, and it's got a charge of Q. What they want us to do in this question here is determine the change in electric potential energy, which is delta U, of the proton sphere system when the proton has moved through a 20 volt potential difference. So the potential difference between each iso line was 10. So this VA was 60, then this one's 70, and this is 80. So a 20 volt potential difference is going to be when the positive charge, because the positive charge wants to move to the right, right? It wants to move away from this positive point charge. So this is going to be, this point right here is when it's traveled through a 20 volt potential difference. So how do we calculate the change of potential energy for that journey? The way you do it is you use the definition of potential difference. So the change of potential energy is going to be the potential difference times the charge. So change is always final minus initial. So final is VA, initial is VB. So this is going to be VA minus VB times the charge. And this is the answer to this one. Okay, second part, as it moves through the 20 volt potential difference, the proton was displaced a distance d by the electric force. Determine a symbolic expression for the work. Okay, my tablet does not let me erase, so I'm going to do this. I'm going to redraw this part right here. Okay, so let's look at this now from a work perspective. So as the positive charge Q, as it moves from point B to point A, the electric field exerts a force. And that's the only force on it. We're ignoring gravitational force here because it's negligible compared to the strength of the electric field. So what we can say using our definition of electric field. So definition of electric field is force per charge. So therefore, the force of an electric field is equal to charge multiplied by the electric field. Now, do be aware, as this positive charge moves down the electric field, as it goes down the electric field is not constant. And the reason why is we're moving away from this point charge over here. It's just like if you move away from the Earth, the gravitational field does not stay constant. But we're fine because they're allowing us to use the average electric field, right? The electric field at B is going to be stronger than the electric field at A, but let's just use the average. So we can say that the average force is going to equal the charge multiplied by the average electric field. Now we can very easily calculate the work. So they told us that the distance moved was d. Work equation is force times distance. So therefore, the work of the electric field is going to be force, which is QE average times distance. And that is the answer to this one. Okay, we are at the end. This part here, let me revert this. Okay, so we have two students discussing. I always love this because I know kids sit around discussing these problems. Well, actually, I hope they do. Students are discussing how and why the kinetic energy of the proton would change after it is released. So the proton starts here at B, and it's going to move to A. Student 1 says that if the system is defined as the proton and the spheres, all right, so they're saying the system is all of these charges, right? And keep in mind, charge X and charge Y are creating these isolines. And then the proton is a charge that's placed into the system and travels from one isoline to the next. So student 1 says that if the system is defined as these three charges, the increase in the kinetic energy is due to a change in the system's potential energy. This would absolutely 100% be true because in order for this proton to have potential energy in the first place, it needs to be the system must include other charges to provide that potential energy. I mean, if you just had a proton by itself you know, how would that proton even have potential energy? In order to have potential energy, there has to be another charge that, you know, within the system. So now we can talk about, you know, oh, this charge now has potential energy due to the other charge. So that is correct. You could say that the proton's gain of kinetic comes from the system's loss of potential energy. Student 2 then says, if the system is defined as only the proton, so that's back to this, so here's a proton with nothing else in the system, the kinetic energy of the proton increases because positive work is done on the proton by the electric field. So here the electric field is acting as an outside force. So in order for this proton to gain kinetic energy, you know, if it's in a system by itself, what would cause this proton to gain kinetic energy? There would have to be some force applied from the outside, from outside the system, right? A force is going to come in from outside the system and cause this proton to accelerate. Now, where would that force be coming from? That force would be coming from sphere X and sphere Y, which are sitting outside the system. So both students are correct.